So hopefully that issue with my laptop is now fixed. So we'll get back to the pipeline part. So as we had before, so we have this amazing algorithm that gets 100%, but in fact, when we give it a digit that it hasn't seen before, it gives us sort of the wrong answer. And so clearly, this isn't a perfect algorithm, and there's lots of things we could do to improve it, and we have to pick better ways of evaluating that. So this is where this idea of training, validation, and testing comes in. We won't talk about that specifically in this lecture. We'll cover that in one of the later ones, but that there are ways for trying to split these things up that help us deal with this problem a bit better. We'll leave out logistic regression. So regression is very similar to classification, as we mentioned before, but the difference is instead of trying to predict a class that you output in, you predict a value. And so, it's really a continuous problem instead of a discrete problem. So for all of those of you who've taken sort of signal processing classes, it's the difference between sort of a Fourier transform and a discrete Fourier transform, that one of them handles continuous space and acts like everything is sort of on one single spectrum, and the other one handles a number of very discrete conditions. And so we can take, luckily with this data set, the exact same tasks of the digits, and instead of predicting a category, we can predict the actual number. So we have the model output a number between 0 and 9, where it can also output fractions. So it could output 9.2. Probably that for this case doesn't make a lot of sense because, a 9 doesn't look anything like an 8 doesn't look anything like a 9. So 8.5, implying that it was somehow between 8 and 9, doesn't really fit for what we're trying to do. But potentially in how we're penalizing the system, it makes more sense. So again, we have this idea. We split the data this time into the first 50 we use for training, and the next 450 we use for validation. And so we just split them this way. We know the data set doesn't have any repeated digits, so it's okay. We can then put it in our sort of simple pipeline, and this time instead of having k neighbor classifier, we have k neighbors regressor. And so that's I think one of the really important things to appreciate with tools like scikit-learn and KNIME, that changing from a regressor to a classifier and changing from k-means to linear regression, k-neighbors to linear regression to random forest to decision tree just involves tiny switches in your code. It doesn't involve redoing everything from the beginning, re-implementing anything. It doesn't involve compiling, that everything's there. And that's how you should think about doing these kinds of models, in that you pick sort of your model based on what works the best and deals best with the problem you give it, rather than what function happens to be implemented in the toolbox that you're using. So this is really where regression gets very different from classification, and this is potentially the most important difference to really understand there, is that when we were doing classification, what we were focused on was, accuracy, and that obviously has no meaning for regression. That we're no longer dealing with accuracy. We don't have precision or recall. We don't have ROC curves we can look at and try to optimize. What we have is we have a predicted value and an actual value. And so what we use for this typically are sort of mean squared error and mean absolute error. Of course, there's lots of other metrics you could look at and come up with, but that fundamentally we penalize by how different the value is from the value that we predicted from the value that it's supposed to be. And that's how we assess these systems. So can anyone think of why for the digits problem regression might make more sense? In terms of the assessment or the penalties that we apply?
Because you have one here, like the digits can have different range, like there's not one particular amount of pixels that should be represented for the different classes. So I mean regression could fit better since you have freedom when you write, right? So I mean for example one, you could do it like this.
Yeah.
So just a straight line. I don't know.
Yeah, I mean, so having a model, I mean, that's one of the things the digits things really brings in is a data set that you have a one that's written like this, you have ones that are written like this, you have ones that are written like this, and you have sevens that are written like this with a tiny thing. So there's a lot of sort of rotational insensitivity. In some cases, linear models can be less sensitive, that when you're making a linear model based on like the length, that would be potentially a better fit than just looking at directly the pixels. But in terms of when we're thinking about accuracy versus MAE, why would one be better than the other?
Maybe because MSE is really sensitive to outliers.
Yeah, so it's sensitive to outliers, and so it's squared difference. And then there's just with MAE or any of them, any reason why that would be compared to just classifying? If you were a bank, what would you want to optimize?
Money.
Yeah, well, yes. And so money,
Your class function. I mean here, if you take the first one, it's basically the first one. It will, if you take the derivative of the log likelihood, you will have you will be able you can easily.
yeah. I think you're thinking too complicated about it in terms of smooth derivatives and that. Do you?
To reduce false positive, and then if you want to segment numbers, it's
Yeah.
important to understand for 1 for 7, you should have to keep in mind.
Yeah, right. So that's it. So with money, what really comes in, if you're making a check, if I classify one as a 2 in a classifying system, that's wrong. That's just as wrong as classifying a 1 as a 9. But if I'm a bank and I'm reading checks, classifying a 1 as a 9 is a much bigger problem for me because that's potentially 9 times as much money that I'm getting wrong than if I classify a 1 as a 2. So that's where that sort of, when you think about kind of, am I using a linear model? Am I using regression? Am I using classification? That a lot of the things that come in is how are you penalizing your model? And, calling a dog a cat or calling a dog a fish is probably the same. It's not very inaccurate. Or, it doesn't matter too much. And so those categories are kind of equal. Whereas, if you have a regression problem, the further off you are, the more penalized you get. And as you said, if you have the MSE, then it really, really penalizes outliers. And so depending on how much outliers actually cost you or how much they damage what you're doing, it might be important to use mean squared error over mean absolute error. But these are all the kind of things you want to consider when you're doing these problems of kind of what is the metric you're trying to improve. With the segmentation, we had the ROC curve. We had this idea of false positive, false negatives that we could work on. And when you're doing these kinds of problems, the real important part is to not simply build a model and say, look, it works, but to know how you can assess this. Yeah?
Let's say you're classifying letters instead of numbers. How do you measure predicted minus actual?
Right. So for letters, this would make a regression model probably wouldn't make very much sense. You'd probably use just classification because that would fit. But a lot of times when you're doing problems, it's unclear if you do a classification or if you do a regression. And sort of doing that kind of thought of what are you actually trying to do and what do you suffer from, where is an important consideration to make. So for letters and text, you have entirely different things that you penalize. You look at, did the letters match, or more importantly, did the words that you output mean the same thing? That, if you say it was a very good day or it was a quite good day, those probably mean about the same thing. And so you shouldn't penalize it, even though very and quite are different letters and don't match up at all. And so with text, and we won't get into that at all, but you have kind of entirely different things you need to take into account because just applying these simple metrics doesn't work very well. And this is what you'll see on places like Kaggle, that sort of the guys who've downloaded TensorFlow and installed it and can compile models really quickly but have no idea about statistics or fundamentally what they're doing will, use mean average error function on a text classification problem, where anyone who was thinking about the problem carefully would go, that doesn't make any sense. It's a very bad penalty to use. You might be able to make a reasonable model, but you're limiting yourself by the fact that you're sort of adding this nonsensical thing to what you're trying to do. And so those are sort of the things that are quite important to remember. And there's a lot of problems where it's not easy to see if it's a regression problem or if it's a classification problem. If you're an insurance company and you're trying to predict, claims or how many people are going to make claims for expensive damage, that could be a classification, a true-false event, or it could be how much does that cost you, and that's what you're then trying to minimize for. And, picking that right metric isn't simple. So we can do this for digits again, where we now have it predict. So we make our pipeline up there, or I think our pipeline we made here, where we had flatten, normalize, nearest neighbor. And then what we end up with is on the training data set, as we expect. We have this perfect curve where it predicts everything correctly because it does nearest neighbor. There's no reason it would do anything else. And then we have on the validation set sort of a mean squared error of 1.7 and a mean average error of 0.4. And so since all the points are stacked on top of each other, you don't really see in detail what's going on, but you can measure how well that system works. And if this was, again, a bank, you would be more interested in that mean average absolute error than you would be in the accuracy. Because the accuracy doesn't really tell you how much it will cost you, it just tells you a lot of things were inaccurate. And this now gives you a better idea of how far off you might actually be from what you're trying to do. And so now to actually move into the interesting part of this, or why we covered these techniques in the first place. This isn't a machine learning course. This isn't a statistics course. We fundamentally are trying to solve problems. And so we have this brain cortex problem like we talked about before. And if you remember from the basic segmentation and advanced segmentation, we really had no solution for this. We talked about a number of different methods. We showed some approaches, but we really didn't fundamentally find something that did a reasonable job of segmenting this image. It's difficult to see. There's not really a threshold that makes it work perfectly. And so it's a hard problem. And so we show the images here where we have that image and we have this ground truth label of what we're actually trying to segment. We can then split it up. So this is a very poor way to do it, but not a bad starting point for just testing out ideas. And so what we do here is we just sort of take a cut. So we take the first 100, I think, columns. Yeah, columns of the data and say that that belongs to the training data set. And then we take the last part and say that belongs to the validation data set. So we try to sort of train on part of the image and then apply it to the whole image and see how well it works. You're, of course, biased here by the fact that you're just looking at one image, and so you don't know that it would necessarily work great on a completely different image. But for getting a reasonable approximation of is this technique fundamentally looking at the right things, it's not a terrible starting point. So now you end up with your train image here and your validation image there. And so they cover different parts. There's no overlapping pixels in them. And so if you can come up with a metric that does, or a technique that does that well, you might solve the problem. So we can build a pipeline just like we did before. We have a different flatten step here. So we have a pixel flatten step, which is what's necessary for segmentation because we're not trying to take all of the pixels and put them into a group. What we're trying to do with the segmentation task is want to say for each pixel what class that belongs in or what value that should have in this case. And so here we flatten it so that each pixel is its own instance. We then normalize the data, and then we create sort of a random forest. And so when you look at what we start off with, the input data is this image, 173 by 100, so that training data. Step one, this pixel flatten, changes the dimension, so we now have 173,000 things. 17,300 things we're trying to classify correctly. And then the normalize step, and then we try to classify them into the right group based on this mask that we have before. Here we use random forest, maybe to make it easier. We can just use. So we can switch that method to use a method that we actually covered before. Yep, so now we have the decision tree. We can then show the decision tree as a that works. If we go back here, just go show tree. Yeah, so that if we showed the tree there, we can now see what we trained the model on, and basically what it did, because all it was given for each pixel was the intensity after normalization, is it said if it's below 0.5, it's in this class, and if it's above, it's in this class, it having 46. And so that model then learned to classify the images to try to sort of minimize that mean squared error, because that was the problem we gave it to do. So we can now show this, and we see sort of the classification that we get. And so what it does, which it's a little bit difficult to see here, is it's unable to find a gray value, which is kind of what this tree told us, that perfectly segments everything. And so it decides to basically paint the whole image, more or less, at this 46 value. And so it tries to minimize that mean squared error. So rather than going for saying everything belongs to the cortex, it sort of gives you this middle response of, well, everything there could kind of belong to the cortex. So it doesn't paint it bright white, so the same color there. It paints it sort of this intermediate value, because it wasn't able to find a single grayscale value that did that. And so, using a, decision tree regressor on pixel level data is very similar to what we did with the approach of automated threshold finding. The difference is that rather than being dependent on some model like isodata or some model like Otsu, you have the training data which you use to drive what you're trying to do. And so here we know what it's actually supposed to look like, and we then fit a model to make that prediction for us. And so now what we can do is sort of go one step further, where we add position information into what we're doing. And so rather than having this XY step, you don't have to worry how it's done, but basically you add position information into the image so that you keep track of where you are in the image, and you add that as sort of an additional variable. And so that you'll see here we go from 173 by 100 to 173 by 100 by 3. And so next to every pixel you have the location in X and Y that pixel falls into. You can then do this pixel flatten, which gives us 17,300 instances that we're trying to train. Each one of them has 3 values associated with it. So this X, this Y, and the intensity. We can then normalize and perform, we'll leave k-means out for here. I think that's potentially in the next step. We can then normalize it and then see that we get sort of the intensity values here, and then we have the position values there. We can now apply this technique, and we get a significantly better guess, because it's able to incorporate the fact that if it's in the top half of the image, it's much more likely to be cortex, and if it's sort of over in this corner versus over in that corner, it's more likely as well. Yeah? Yes, so if you rotate or translate the image here, it will then completely fail, because it's now learned that sort of the X and Y coordinates are important for identifying that part of the image, that cortex region. So with that, if you have all of your brain scans registered, because you always know the front of the brain is here, the back is there, the skull is very easy to find, then you can use a technique like this where you take the X and Y coordinates to sort of do a better job of segmenting it. But if you have a problem where sort of the organs could be anywhere, you have tall people, you have short people, fat people, thin people, then incorporating the position wouldn't necessarily improve your algorithm. And so you do have to be aware that it's sort of a cheap fix to a problem that can make it work better, but involves some risks that you want to be careful about later. And so for this, of course, we weren't trying to fundamentally completely solve the problem for everything. Yeah?
Would it be correct to say that it's memorizing more than learning in this particular situation? It's memorizing from the training images and just reproducing actually generalizing well on the data set.
Yeah, so this would definitely not be an example of where algorithms really understand something very well. But this can be quite useful if you have 1,000 scans that look very similar to this, and you want a way of getting the cortex out of them, so that you can have it not simply just based on the X and Y, and clearly we only did this with one image. If you started to train these models with 5 or 10 images, it would then be less sensitive to those individual shifts or translations. And so here with just one image, I mean, anytime you do anything with one image, you're probably not learning. You're probably just memorizing. And so, yeah, you would, probably calling this machine learning would be too much. It's just sort of a, how do you apply these techniques to these images to get results? Where I think there are a number of these techniques, and the difficulty you run into most times is that it's very difficult to apply them to image data. You know, if you search for random forest segmentation of images, you'll find lots of papers. You'll find almost no tools available for actually applying this to real data sets. And so that's where it sort of becomes difficult to use. You can then keep stacking things in. So just like you do with normal scikit-learn, you can add sort of k-means here. And so you can run that, where it now does a normalization. It does a k-means, and so it brings them into different groups, and then handles each one of the groups separately, and then you end up with sort of slightly better, more detailed version. Not quite perfect yet, but a starting point for what we're trying to do in these images. And so here, really the point is not that this is the best solution for your problem, but this is how you start exploring these kinds of approaches. And then of course, you know, rather than adding position, you could add texture. You know, you could add the output of an edge filter. You could add Gaussian filters in order to get richer information there for making those sort of segmentation decisions. And so there's a lot of different ways you can incorporate more information. Position is probably the worst one for a lot of tasks because things tend to shift around and move, but it can be a very useful one. You know, if you're looking at a human body, you know that, you know, the lungs are next to the heart. And so if you can figure out where the heart is, you can probably figure out where the lungs should be. You know that there shouldn't be a brain in someone's foot. And so incorporating some information on that can make your task a lot easier rather than sort of starting off each point blindly guessing what it could be. We can then add these whole poly features that we talked about before. So where you add sort of combinations of position, intensity, and everything else together. We can do this third degree, where we end up with, you know, going from 3 features for each pixel to 20 features for each pixel, which is really quite a few. And then we get here and we get sort of an even better segmentation of what we were trying to get originally. And so by playing around with these pipelines and tweaking what you do, you can get sort of continually improving performance on these kinds of tasks. And so this was sort of a brief introduction to how these techniques work and how they work for sort of standard imaging. So for those of you who looked at, did anyone do the exercises from last week? No one. Is anyone planning on doing them? A few people. Okay. I mean, the main reason for this is that when you look at neural network approaches and deep learning approaches that exist today, they more or less do steps like this, and they make it very easy to put all of those together. And what it's important to be able to do is to be able to say, I can build a simple, trivial approach the same way as sort of my baseline or my comparison. And that right now, the work to build a baseline approach is much harder than the work to build a neural network approach. And so most people just build a neural network and say that this is more exciting anyways and completely forget that aspect. And so I think it's important to appreciate how these techniques that we call sort of standard machine learning work and what kind of results you can get with them before sort of diving headfirst into the whole world of machine learning, because there are lots of problems that you can't solve with a simple threshold. That's clear, but not every problem requires a giant neural network in order to get a good solution. And sort of being able to have a wide variety of different tools you can apply and tools that you actually understand. I mean, while no one would argue that this tree is super easy to understand here, it's, if you just focus on the simple question, it's fairly straightforward to know what this model's doing and what it's responding to. And we can do sort of the same, we can actually do the same thing for once we add the position information, which is potentially more interesting. Oh. But you can show the, so you can see that we have 170,000 points that go through. And so building a tree for this hasn't been optimized particularly well. So random forest works much faster, but building a tree lets us actually see what happened. And so for this, we're able to go through and see for each decision it made about a pixel, what information it took into account. And so the most important decisions are, of course, at the top, where we're able to look at sort of the true, the false, and follow down what pieces of information it was incorporating. And as we see here, because we've normalized the variables, a lot of the decision criteria don't appear very interesting because a lot of them just get rounded off at 0.0. But that we can see, x1, x2, and x0. So x0 is the actual image data, x1 is the x-coordinate, x2 is the y-coordinate, and we see almost no information on the x-coordinate and the y-coordinate, on the intensity, and we see all information on the x-coordinate and the y-coordinate. And so going back to your point, this is probably an example of something that has learned very well about the positions in the image and potentially has not learned very much about what actually a cortex is. And so it's probably done a lot more memorization than what it should do. And of course, if you take machine learning courses, you'll learn a lot more about how these trees are actually made, how you can improve the process for making the tree, how you can go through and delete parts of the tree that aren't helping your classification get better, what sort of these different indices like Gini and some of those other that we showed before mean. But for this, it's really just about how do you have a basic feeling for these tools and know how to apply them to different kinds of problems. Because even though neural networks are more complicated than this, they're not really doing much different kinds of steps than these are. And so appreciating what's possible with these tools, I think, is quite important. It's over here. Yeah, some of them don't render very well. Wow. Okay. Yeah. Anyways, you end up with, particularly because we have so many different pixels we're putting in. So for one image, it was 17,000. It's able to learn lots and lots of different very weird rules for classifying these images. And many of those, as we've seen in sort of the results, are not the rules we would hope a system like this would learn. So are there any questions on that? Okay, so the next lecture will then be on sort of the single object and multiple object, and simple and complicated analysis of shape. And so how we incorporate that kind of information, because once you've done the segmentation, it's sort of an important task of what you do with it afterwards. And that's what we'll go to from here. So the next two lectures will sort of be combined, unless, no, I think the next two lectures will be combined to make room for this one. In terms of topics that are coming up, are there any topics people are interested in that don't appear on the course now? I mean, in general, is there an interest for learning more about neural networks or learning more about standard computer vision approaches? Standard. Okay, that's fine. I mean, because there's the issue, of course, that there's not enough time to teach everything that might possibly be interesting. And if you look at the tools that people are using today, people winning contests are not using a whole lot of standard tools. And so it's more about, do you want to learn the more complicated tools that people are less confident about and aren't very, let's say, standing on robust theoretical grounding? Or are you more interested in learning about the robust tools that don't seem to do a good job at any competitions? What? Okay.
I think like whatever is like relevant in today's industrial problems or whatever's used in like companies and stuff is much better. It'll be more relevant to them.
So we should teach blockchain too in this class. Okay. Yeah, I mean, so that's the main reason these things have been added, is because we've seen that the relevance for the standard approaches has dropped wildly. That you don't find jobs where they ask you if you know how an Otsu threshold works. They ask you if you're, a TensorFlow ninja. And so, obviously we can't do that entirely in this course, but making you comfortable and aware of what problems you run into when you do this is quite important. And particularly when you look at the Fachhochschule in Switzerland, all of them are doing these things. They don't really necessarily always understand what's going on, but they're applying these tools to all kinds of different problems. And so it's almost sad to look at ETH and see that the students are learning the nice, robust methods that no one's actually using anywhere. Do you have a question on that? Or? Okay. Well, also feel free to send email or fill out the anonymous survey and say what you want to see more of or what you're more interested in, because there is quite a bit of flexibility in what we show. And the goal is to try to teach you things that will be useful, and ideally not just useful tomorrow, but have some value beyond then. And I think that's where the things like assessment come in, because no matter what kind of neural network or classification approach you're using, if you don't think about assessment, you'll probably not get very good results. And as you've seen with sort of the exciting papers, Google has networks now that build networks. So they don't need you to write the code for the models anymore. They can do that themselves. But they still need someone to decide if the network does a good job, or how you define a good job, or what's important to get correct. And so that higher level understanding, I think, will be important for quite a while. And the actual details, I think, will get less and less important. I mean, even Facebook, with a lot of their projects, they automatically generate the most efficient computer code for any project you're doing by trying out millions of different variations and keeping the one that works best. And so it's not someone hand coding C++ or hand coding CUDA. It's people writing tools that figure out how to do that well. So